Today we talk quadratic inequalities, and basically what we're going to be looking to do is, rather than just solve a problem like an equality, for instance, in this specific example, if we were to solve this like an equality, I would have x minus 4, x plus 3 would be equal to 0. I'm going to throw my greater than in right now just to let you know. We'd say 4 and negative 3 are my solutions. But in this case, we want to know when the value of this function is greater than or equal to 0. So this brings this whole idea of a quadratic into play. Now, what we found really is we found intercepts. So I have intercepts of 4 and negative 3. And in this particular quadratic, it's a parabola that goes up. And what they're asking us to do is say, when is the value of the function, in other words, when are the y values of this function greater than 0? Well, the y values are represented by the actual blue. And so where are they greater than 0 or positive? And that's in these regions right here. Now, I could state those regions as simply as saying, well, that happens from 4 to infinity, and from negative infinity to 3. What happens if I didn't have a graph to look at? How do we figure this out? Well, these are not only intercepts, they call them critical numbers. And these are the numbers at which the graph does something like crosses an axis or switches from moving upwards to downwards. They're just important numbers that we have to look at. So what I'm going to do is I'm going to list those numbers, if you will, on a number line. So here's negative 3, and here's negative 4. And something drastic is going to happen to the curve when I hit these numbers. Something's going to change about it, possibly. So in this case, what I'm going to do is I'm going to see, okay, well, what's happening with the curve to the left of negative 3? What's happening with the curve between negative 3 and 4? And what's happening with the curve to the right of 4? And we can see that over here, but I'm just saying, what if I didn't have a graph? So in order to do that, I'm going to see what are some values to the left and right of these points. So to the right of 4, I have like 5. In between 3 and 4, I have 0. And to the right of negative 3, I have like negative 4. And what I'm going to do is I'm going to see what kind of values pop out of the function when I plug these values in. And where am I going to plug them? I'm going to go right into this factored form. So you'll notice, and I'll do it for one and then I'll be more general for the others. If I were to plug negative 4 into this factored equation, I would have negative 8 times negative 1, which is 8. That ends up being a positive number, which we would expect by our graph over here. And that positive number is greater than 0, so this satisfies our inequality. If I plug in 0, notice I get negative 4, which is a negative number. And this is how I'm going to do it from now on. And a positive 3, which is a positive number. And if I multiply those two together, I get a negative number. This does not satisfy our inequality. If I plug in a 5, I get 5 minus 4, which is a positive 1 or a positive number, and 5 plus 3, which is 8 or a positive number. Multiply those positive numbers together, get a positive number, and that satisfies our inequality. So then I can state, well, all the numbers to the left of negative 3 are in my solution, and all the numbers to the right of 4 are in my solution, which we already knew from the graph, but we're doing it again without a graph. So let's go to the next example. And in this case, we have our inequality. I'm not a big fan of factoring with negatives, so I'm going to bring that over to the other side and say I've got 6x squared plus 17x plus 5 is less than or equal to 0. I'm going to take and factor that using a 5-step. So I'll multiply the 6 to the 5 and get a 30. Factor into x plus 15 and x plus 2. Divide by the 6. Get 5 halves and 1/3. Bring the denominators forward, get 2x plus 5 and 3x plus 1, leaving me with critical numbers of negative 5 halves and negative 1/3. So if I were to look now at a number line and say, okay, now I need to pick some numbers outside of these regions and between the two regions, what number should I pick? I'm going to go with negative 3 here, negative 1 here, and let's go 0 here. When I plug a 0 in, once again I'm going into this equation, I get a positive and a positive, which is a positive. That fails the inequality test. These numbers, that number, a positive number, is not less than 0. So I'm going to say no to this. When I plug a negative 1 in, I get a positive and a negative, which is a negative. So that satisfies my inequality. And then plugging a negative 3 in, I get a negative and a negative, which is a positive, and that fails my inequality. So I can state that only in this region here do I get the solutions that are less than 0. So I'll say, and it's less than or equal to, so I'll say negative 5 halves to negative 1/3, include both, and that's my solution. If I look at the graph of this once again, here are my intercepts. Here's negative 1/3, here's negative 5 halves. It's an upwards opening parabola. Where are those values? Less than 0 or below the axis, right here, and that mimics my solution. Wouldn't be a lesson without a word problem. So here's a word problem. Why don't you pause this, take a minute to read it, and then we'll go through it. So you'll notice that in this case, we have a set of axes here. And what this equation is describing is the height of the water relative to this arc. And the base of the arc is down here, the vertex up here. So they want us to write an equation that approximates the possible water levels below the parabolic arc. Okay? And once again, they're talking about a level of 0 here. So what we're asked to do is write an inequality, basically. Now I know that I can use f of x, g of x, doesn't matter. But we want to know when y is greater than or equal to, because the water would be rising above the arc, negative 0.03x squared plus 0.84x minus 0.08. And that's going to tell me when this water starts rising above the base of the arc. Now, they want to know, let's see, in part B, they want to say the water level is at most 0.2 meters high. That means this line going across has a distance of 0.2 meters up that arc, if you will. So we want to know when this graph is above 0.2. And they want us to go ahead and solve that. But to do that, I think we're going to use our calculator. So why don't you get that out as I'm continuing to write this and start plugging in the formula. So let's do that. So here's the equation. And let's take a look at the window that I used. so we're all on the same page. I went from -10 to 30 because I got a feeling this is going to be pretty wide. And I'll still go from -10 to 10. Let's see what happens. And we'll graph this. And you'll notice that my entire picture fits in the window. So this is mimicking the picture over on the left. And what I'm also going to do is, since I want to solve this, I'm going to pop in a y equals 0.2 for a second equation, because I'm going to look to find the intercepts. That's going to get me my critical numbers. Then I'll graph that again. Now you'll see that's really difficult to go ahead and view. So I'm going to blow this up a little bit, all right, in a zoom box. So I'll do the following. Or actually, let's not. Let's do this. Let's make our window a little taller. We don't need to see all that negative stuff. So we'll go window, and we'll go from -1 to, let's go, I want to see that gap a little more. Let's just go to 4. And it's going to cut off the maximum part of this graph, but I'm going to be able to see the 0.2 a little bit better. So there's my 0.2. So I can see now that it's 0.2 up that arch. And I want to find out where are these important numbers. So we're going to take and calculate an intersection, 5. And I want that blinking piece to show up somewhere. And it looks like it's right there, so I'm going to hit enter 3 times. And that's going to happen at roughly, well, maybe it's not going to happen. Let's try it again. Intersect. 1, 2, 3. At 27.66. And then let's find the other side. And we've got second calculate intersect. And we're going to move all the way over. It'll take a second to get there. There it is. I'm going to hit enter 3 times. And 0.33. 0.34, let's say. So these are my critical numbers. And we notice the graph looked like this, and we were above here. So once again, if those are my critical numbers, and where is this greater, it's in between that interval. All right. So to solve that inequality, we want to know when is it at most 2 meters high between these 2 points. So we could say, well, when the x value is at 0.34 and 27.66, it's 2 meters high, and they want to know the width of the river under the arch when that time happens. To find that width, well, basically we're just taking and subtracting these 2 x values. So if I take, this is part B, part C, if I just take 27.66 and subtract off 0.34, I'm going to get my answer. So 27.66 minus 0.34 gives us a width of 27.32. Is that meters? I want to say meters, yes. All right, and that's all we've got. So moral of the story, set aside equal to 0, find your critical numbers, do your testing between the intercepts, and then state the answer. Go to my math lab, get the problems done, and we'll see you tomorrow.